Hello everyone, welcome to the lab 1 of ECE 573 Advanced Embedded Logic Design. In the first lab, we will discuss a very basic example on how to run the simple C code on the Zynq SOC platform, and specifically we are using the zedboard platform. So in this lab, we will discuss the architecture of the Zynq SOC in very brief. For detailed architecture, please refer to the lecture video. And we will learn how to program the ARM processor so that we can communicate the data in both the direction with the UART terminal. And specifically, we will use the simple hello world example and then the FFT example. For the regular labs, we will use the Vivado 2019.1 along with the software development kit SDK. In case you are using the advanced Vivado, say 2021.1 or 2, we will add a separate add-on video to discuss the difference between both the Vivado version. In this lab, we will explore the basic Zynq architecture, how the Zynq configuration is done, then how to use the Vivado to create a project when only the ARM processor of the Zynq is used, then write an application, C-based application, which will be executed on the ARM processor, then how to verify the performance of your applications on the hardware. We will discuss two cases: when you have the physical access to board and when you have the remote access to board. Okay. Then we will discuss how the debugging is done by using the breakpoint variable registers in the software SDK. And then there will be additional video to discuss the extension of our lab for the Vivado 2021.2. So prerequisites, make sure that you have the Vivado with the SDK install on your laptop. In case you have the local access to the board, then make sure your board is working fine. In case you have the remote access to the board, make sure you have the appropriate IP address and the port number with you. Then to use the board, to use the zedboard, which is from the Digilent, you need to add the corresponding files, board files, and the details are given on this link. We have already shared the handout explaining the process. So this Zynq SOC, which we are going to use in our lab, is a heterogeneous, all programmable system on chip. So in this case, you have the two components. One is the processing system, which is called as a PS, and then second is the programmable logic, which is called as a PL. So this processing system is nothing but the ARM Cortex A9, which is the dual core ARM processor, while this programmable logic is the 7 series FPGA. In the today's lab, we are not going to use the PL logic. So for us, this part is irrelevant. So we are going to use the one of the core of the ARM processor. So we will use the core 0. Then we are going to use the one of the peripheral. So we will use the UART, and our application code will be stored in the external memory, which is nothing but the DDR memory. So we will use the memory interface. So this is what we are going to use in our lab. Now, to give the slightly more details about the Zynq SOC, it is not just a FPGA, it is not just a microprocessor. It is the unique blend of two technologies with the powerful interconnect. Again, the more details about the architecture we will discuss during our lecture session. In the Zynq SOC which we are using, we have the ARM Cortex A9, which is the application grade processor, which has been used in multiple mobile phones, tablets in the past few years, and it's very powerful processor. You can implement the entire operating system Linux on this processor, while the FPGA is the one of the latest 7 series FPGA architecture. Again, for the AELD course, we don't need to worry about the FPGA architecture. We will use it as a black box. Now here, this is the heterogeneous SOC. You need to program the hardware, which is the FPGA, and you need to program the software, which is the ARM processor. So in the lecture, we have already discussed the concept of the hardware, software, co-design. So here we need to divide our application in the hardware and the software. So we need to map the part which to be implemented on the hardware separately, and the part which needs to be implemented on the software separately, and then integrate them together. In the lab one, we are not going to use the hardware anything. So we have only the software part to be taken care. So in the today's one, it is only the software design we are going to do and not the hardware design. Okay. So even though we are doing the software design, but we need to some details from the hardware side to understand which part of the our Zynq SOC we are going to enable and disable. To understand this in more detail, as we know, we have this Zynq SOC, we have the ARM processor, and then we have the FPGA here. Now, as we seen in the previous diagram, in the Zynq SOC which we have, there are multiple peripherals are there. For example, there is a UART is there, then there is a SD card is there, then Ethernet is there, then you have the serial peripheral interface is there, I2C bus is there, but we don't need all of them. So we need to configure our, we need to tell when we configure our board, we need to make sure that we disable the components which we are not going to use. For example, there will be flash memory is there, which we are not going to use. So we need to disable this thing. So this part we need to take care while doing the lab. Okay. So in our lab, as a hardware, as a tool, we are going to use the two tools. One is the Vivado and the second is the SDK. Using the Vivado, we are going to configure our processor peripherals, like we are going to disable the peripherals which are not going to use, and we are going to enable the peripherals which we are going to use. Also in the Vivado, we are going to develop the algorithms which needs to be implemented on the PL. So we will develop the corresponding IP and we will integrate with the corresponding ARM processor via AXI interface. So all these things will be done using the Vivado, and inside the SDK, we will write the application which needs to be executed on the ARM processor. So SDK is used only to write the application which will be implemented on the ARM processor. But to make that application run, we need to generate the we need to enable the appropriate units in the hardware, and everything is done using the Vivado. So to understand this in graphically, using the Vivado, we generate the hardware-based system by configuring the appropriate unit in the hardware, which include the PS as well as PS. Then we pass this data to the SDK, where it is referred to as a board support package. So it has all the drivers and the necessary files, which allows your applications, which will be running on the processor, to communicate with the hardware, like UART, your memory, your accelerator inside the FPGA. So everything, all the drivers are automatically generated and which are there in the board support package. Then you can implement the entire operating system on the ARM processor, and then you can write an application on the operating system. But in our course, we are not going to use this option, but instead of this, what we are going to use, we are going to write a simple application, and this is called as a bare metal code. So it is without any operating system. It is a simple operation which will write it in the C code, and that gets converted into the assembly code, and it will be executed by your ARM processor. Okay, so ours is much simpler version of the things which can do on the Zynq SOC. So board support package, it consists of the set of low-level drivers and the functions that are used by the next layer, like operating system or the application in the OS or your bare metal code to communicate with the hardware. Software application run on the top of the operating system, and these collectively represent the uppermost layer. So if you are using the operating system, you write application on the operating system which can communicate with the hardware. SDK along with the Vivado provides the environment for creating the BSP. So this board support package is created using the information which is communicated from the Vivado to the SDK. And then your application is written inside the SDK. Board support package includes the hardware parameters, device drivers, low-level OS function, which are enabled in the hardware, so that all the things are automatically generated and provided to the SDK. So whenever you make any changes in the hardware, for example, in the beginning, today's lab, we are using only UART. So we might disable the USB SD card. But suppose in the lab 2, we decide to use the SD card. So in that case, we can't use the board support package which was used in the previous lab. We need to refresh our board support package, or we need to regenerate our board support package. Then there are two files are generated. One is the ELF file, and the second is the bit file. So this bit file is used to program the FPGA, and this ELF file is used to program the ARM processor. In the today's lab, we are going to use only the ARM processor, so we are going to generate the ELF file and we are not going to generate the bit file. So the purpose of ELF file is to program the PS, while the purpose of bit file to program the FPGA. So not all the designs require both the files. ELF full form is executable linkable format. So not all the design need both the files. For example, in the today we need only ELF file. If tomorrow you are using only the FPGA, you will need only the bit file. You won't need a ELF file. Okay. So if only one part of the Zynq device is used, then only the corresponding file format is needed. Okay. So to summarize, in the today's lab, we are going to use only PS part of your Zynq SOC, that is only the ARM processor. We are going to write a C code which will be converted into the assembly language code, and then which will be executed by your ARM processor. So this C code will be to write this C code and implement on the ARM processor. We are going to use the SDK, but before we use the SDK, we need to use the Vivado to configure the hardware to enable or disable the different parts of the hardware. Okay, so this is what it's seen here. We are going to ignore everything here. Then we are going to use only the UART here. So we are going to disable everything, and we are going to use the DDR memory. Okay, so you can see that out of all the features available are there, we are going to use only these features in the today's lab. Also, among the ARM core, we are going to use only the core 0. So in our lab, what are the steps? The first step is that we need to configure the hardware. What do you mean by configure the hardware? We need to enable or the disable different units which are by default provided on the Zynq SOC. And where we are going to do it, we are going to do in the Vivado. Okay. Then we are going to export the data. Data from the Vivado to the hardware. Okay, so we are going to export the data from the Vivado to the SDK. Then in the SDK, first step we are going to do is that we are going to create a board support package which has all the drivers as well as simple functions which will help us to communicate the different units in the hardware. For example, if you are using the UART, you don't need to write the UART hard drivers on your own. The tool automatically creates the UART driver, So that only thing you need to understand is how to use the corresponding driver. Then you need to write your application. Okay, you need to write your application which will be executed on the ARM processor. So this application is nothing but the C code which will be converted into the assembly language code, and then the ARM processor, and this assembly language code will be stored in your DDR memory, and then the ARM processor takes one instruction, decode the instruction, execute the instruction, and this will be done in the regular fashion. Okay, so we are going to study the two example. One is a very simple hello world example, and the second we are going to study the FFT example. And what we are going to do, we are going to test our design on the hardware remotely, if you have access to the hardware, and then we are going to also see that how to do the debugging in the SDK. So to understand this entire flow for the lab 1, we have prepared the detailed handout which is already shared with you, and in that case all the steps are clearly mentioned. So I don't want to go through these steps here, but I'll just go through quickly these slides so that you are aware about what are the steps you need to do. So you can see that we have added this Zynq IP, which has the details about what are the features are there on the board, and then based upon our requirement, you can see that we are disabling all the things which we don't use to get the only these features where we are going to use the UART and the memory. Okay, so once we do to complete the Vivado steps, once we export the design, then we are going to launch the SDK. In the SDK, again the SDK design flow, we will get all the details which are exported from the Vivado to the SDK. So the details of these files contains all the details about the clock, about the different drivers, and everything is present in these files. Then we will start with creating our application project. So you create application project, give the proper name. So you are using the standalone operating system. We are not using the Ubuntu or Linux operating system. This is the file which we have got it from the Vivado. So we are going to use that one. We are going to use the core 0, C code, and then you can see that we are going to create the board support package. This is automatically will be created. And then in here, after you select all these things, click on next. Okay, and then select the hello world project. Okay, once you select the hello world project, you can see that this project is created along with the corresponding BSP, and you can see that this simple code is there. You can run this code on the board, it will work out and you will get the display on the screen. But instead of this code, we are going to modify this code to get it slightly more functionality. So what we did in our code, you can see that this is the main function in the SDK, or when you implement your code on your processor, main function is the one which will be executed in the beginning. So you can see that here I am defining the 3 variable. One is of the type integer, 32-bit integer. Second of the type single precision floating point, which is 32-bit floating point, and say third is the double precision floating point. Then you can see that here I don't need to develop the driver for the UART. I'll use the stdio.h, and then I'll use the printf statement. So whatever I'm printing, it will be printed on the UART terminal. I don't need this exile printf.h, so you can ignore that one. And then I can also, using the scanf statement, I can also receive the data from the UART, and then I can display it. Now, the problem in the online environment, if you have the physical access to the board, we have discussed how to run this code on the board. It is very simple. You just need to run it directly, and you can use the Terraterm to see the data display on the UART. So in the zedboard, you have the 2 ports, one USB for the JTAG and the second USB for the UART. So you need to use the 2 USB cables, and then you can use the Terraterm to see the display. But we are now working in the remote environment, and our boards are connected inside the university network. So each board has been given a particular address and the IP address and the port number. So using our system, you need to book your slot whenever you need to test your design on the board. Okay. So for all the details, you can contact your TS. Now, by default, your SDK will use the local target, that is local board, in case it is connected. So if you want to use the remote board, make sure you go to the target connection, which is there on the bottom left position. Click on the new target. And then in this new target, you can give any name you want so that you remember that this corresponds to my remote access. Set it as default. Then you will, over the email, you have got the IP address and the port number. Use that first. Then click on the test connection. Make sure that the test connection is successful, and then click on the OK. Okay. After that, now you can see that when you create a hardware, we have enabled the UART. So hardware on the hardware, we have enabled the UART, but now we are accessing the board remotely. So if you want to see the display on the UART, you need to also access the remote desktop, which is not feasible. So what we do, whatever is being passed on the UART from the hardware, we capture those data and then we access it via JTAG terminal. So to do this, what we need to do, we need to go to the system.mss. This file is already open in your SDK project. Click on the modify BST setting, and all the standard inputs and output which are there now go to modify from the UART to the core site. So this core site is nothing but the debugger. It will help us to take the data from the actual board and then get it display on this software. Okay, so this is the way to access the check the what is the data being printed on the UART. So make sure that this is a very important step, and you make sure that you complete it before you do it. Now, here in the remote hardware, to run your code on the Zynq SOC, you have two options. You directly run it so that your entire code gets executed on the board, or you do the debug. In the debug mode, you will your code, after you do the debug operation, your code will be downloaded on the Zynq SOC, and then your core 0 of the ARM processor start executing that code after your download is completed, and then it stopped at the first line of your main function, and then you can do the line by line debug, so you can understand what is happening in the one step. So when you are accessing the remote board, you have to use the debug option. So click on the debug ads, click on the debug configuration. This is very important. Then in the debug configuration, create this new profile for the setting for the system debugger. Then make sure that you select the connection as a remote board. You select the desired hardware platform, and make sure that you click this reset entire system. This is very important. And then click on the debug button. Okay, there will be at the bottom right, there will be a debug option will be there. So click on that. Once you click on that, you will see that your debugger window will open and your code will stop at the first line, your main function. Okay. Now, at this point, you need to make sure that whatever is being, you need to open your JTAG terminal so that you can see your display message on the JTAG terminal. So on the top right, go to the XCST console and then type the JTAG terminal and press enter. And then you will see the one window will pop up. After that, then you can just click on this run button, and then once you click on this run button, you will see that your displays are being you will get the display on this JTAG terminal. Okay, so this is how you need to execute your code. So this is again an arrangement we have done so that you can do the labs same as the physical labs in the remote environment or in the online environment. You can notice that there is a loss of accuracy when you represent the number using the single precision floating point compared to the double precision floating point. Okay, so you can understand the rest of the details. Now, after this initial step, if you are comfortable with this one, we can go to the second example, which is how to implement the FFT on ARM processor. And we are going to take a very simple example. We are going to take the very FFT of size 8, like 8-point FFT. And you can see that in the 8-point FFT, in the butterfly stage, which you might have studied in the signal and system or the DSP, it consists of the 3 butterfly stage. So you can see that this is my input and this is my output. Now, if I want the output in the proper order, normal order, then I need to reorder the input. So I need to have the first x of 0 here, then I have x of 4, then 2, 6, 1, 5, 3, 7. So first thing I need to do is that input reordering, and then I need to have the 3 butterfly stages. Okay, in the first stage of the butterfly, I'll have the 4 butterfly operation. In the second stage, I'll have 2 butterfly, and in the third stage, I'll have the 1 butterfly operation. And the corresponding weights of the butterfly, you can see that it can be calculated easily. Okay, so this is the FFT operation. Understand this figure so that we can discuss the code in the next slide. Now, these weights of the butterfly, they are called as the twiddle factors, and these are the complex value. So to write the C code, it's again a very simple. Everything is same except we'll use the complex dot h because we are using the complex number. So first we define the FFT size parameter of 8, and then we define the constant vector of type float, which is a single precision floating point, and it contains the complex number. And you can then assign the complex value to the twiddle factor. So these are nothing but your 4 twiddle factor, which we have defined it here. Okay. Then we'll write a main function. Inside the main function, again here in this case, I have defined that the input as a fixed one, but you can take the input from the UART also from the user. That is also fine. You can do both way. But here I have defined the input as a float complex, and my output of the FFT will be stored in this variable. And as I told you, there are, before I do the FFT operation, there is a reordering of the input. So what I have defined, I have defined the another variable which stores the reorder data. Okay, so then what I have done, I have done the printing of the FFT inputs so that I'll know what are the input I have passed. So again, I have put them on the UART terminal. Then okay, this slide is slightly jumbled up. So this is the corresponding the MATLAB code if you want to verify your functionality with the MATLAB code. Okay, so then once I do the FFT, so then I need to do the 2 steps. You can see that I'm doing the 2 tasks. First is the input reorder, and the second is the actual FFT operation. And then output of the FFT I am displaying on the UART again. So I am defining the input. You can see I'm defining the input. Then I'm printing the input on the UART. Then I am doing the FFT reordering of the input, then FFT operation, and then I'm displaying the output of the FFT on the UART. Reordering is very simple. You can see that I have defined the reordering vector. So 0, 4, 2, 6. So what I'll do, I'll reorder this one. So data input, I'll take the data output, and data output will have the 0th in the value of the input at the 0th one, then 4th one, then the 2, 6, 1, 5, and so on. So this is a very simple reordering logic. Then the second is the FFT logic. So FFT logic, again, you can see that you can divide into the 3 steps. So there are 3 for loop here: first for loop, second for loop, and the third for loop. In the first for loop, you can see that you have the I is equal to 0, I is less than FFT size, FFT size is 8, and I is equal to I plus 2. So you can see that it will be 0 to 4 and 6. So you can see that it will be executed 4 times, and in 4 times you have implemented this logic. Okay, you can see that there is a plus and the minus to get the corresponding output. Then you have the stage 2. Again, in the stage 2, you are increasing I plus 4, so it will be implemented 2 times. And again, you are doing the same operation which is mentioned here. Okay. Then after the stage 2, you can see that you have the stage 3, which is implemented only one time. So it is implemented only one time. And here you can see that you are doing this complete operation. Okay, so this is how your FFT is implemented on the using the C code. Again, this code may not be the optimized version, but you can always come up with the better version of this code. So if you go into the detail about the stage 1, so you can see that when I is equal to 0, you can see that you are calculating output 0 and the 1. Okay, so you can see that you are getting this output. Then I is equal to I will be I plus 2, so I'll get I is equal to 2. Then you will calculating 2 and 3, so you will get this output and so on. Okay, so this is how the first stage has been implemented. Now in the second stage, you can see that you have the 2 for loops. One is equal to I is equal to 0 to I is equal to 4. So you can see that this will be 0 and this will be 4. So it will be implemented 2 times. So this part and the second part. So when I is equal to 0, you have the j. So when I is equal to 0, you will have the j is equal to 0. Okay, and then you will calculate the corresponding output. Okay, so when I is equal to 0, so you will have the j is equal to 0. So you will calculate first value of 0 and 2. Then you will have j is equal to 1, and then you will calculate the 1 and 3. Okay, so this is how you will calculate all these values. Then I becomes 4. Then you will calculate j is equal to 0. So you will calculate 4 and you will calculate 6. Then you will j becomes 1. Then you will calculate 5 and then you will calculate the 7. Okay, so these all the 4 values will be calculated. Then we come back to the third stage of the FFT, and in the third stage we calculate the final output. So in the third stage, you can see that when I is equal to 0, 1, 2 and 3. So when it is I is equal to 0, you calculate 0 and 4, then you calculate 1 and 5, then you calculate 2 and 6 and the 3 and 7. So this is how it is calculated, but you can come up with another way. So after you execute this one, you will see that the corresponding inputs and output again on the JTAG terminal. Then if you want to see the corresponding assembly language code, you can go to the window, then you can go to the disassembly and you will see the corresponding assembly language code. That also you can visualize it. I'll also in the console window, you can also look at the corresponding variable tab, breakpoint and the register tab, and you will get all those details here. So this will be helpful in the debugging operation. So you can see that this is your entire debugger window. You can see the corresponding assembly language code. You can put the breakpoint or you can run it to the particular line. And at that point, you can see the corresponding variables, corresponding register in the processor. All the operations happens inside the processor register. So you can see the corresponding register value as well. Okay, so this completes the lab 1 of the this semester.